then it's future pointing. It's less than 0, then the other vector is as well.
We think it's something like the time part, let's bring the minus b not q not. Over 1 to b minus over to b. That's why they are saying that in order to make that statement.
Okay, that's right.
Yeah, okay.
So if the time time elements are the product of the
So did you get the solution or did you get it
Yeah.
resolved? Okay.
Yeah, I know it's a lot of different resources have different things because of all index switching sign things.
Yeah. Yeah, that was one thing that was pointed out by Messiers. I mean, probably you guys realized that in the book that was referred to in the problem sheet, it uses a different metric. So if you went and started reading, so that might be some. But x square minus y square is equal to 0 is the same as y square minus x square.
It's because in the book they have time equal to positive and everything else negative.
So how it works out is that sort of a, yeah, most of the, like in physics community, there are two sets of theory people who use relativity a lot, let us say. And one is particle physics people. Particle physics as a field you are familiar with, those who do high energy physics, collider physics, and so on. And the other is general relativity, those who study black holes and cosmology and so on. General relativity people, for various reasons, prefer to have positive sign for space and negative sign for time. And the particle physics people do exactly the opposite, positive for time and negative for space. Now, I have been using the general relativity people's notation, even though by training I'm a particle physicist. I don't know how I know why, because my mentor was using that. So that school of thought has been using that. So I kept using the textbook that.
Changing the covariant contravariant.
No. So let me mention this as we go. I'll talk about that in a minute, because we'll exactly. So let me say a few more things before I reach that. Homework 6 is due Tuesday. That's a recommendation. If you want it to make it Thursday, I don't mind it. But as far as the course goes, that's the deadline, so that I can keep progressing with my course. That's my point. Homework 7 has been posted. It's pretty much the same content, but now there is a spring break, so you go all the way after spring break, and there's 2 weeks. So it was 4 weeks. So hopefully that will finish relativity, and then we come back to what commands. And when is the exam? Do you guys know?
It was 12. May 12th, right? May 12th.
No. I meant for the second midterm.
It's April.
First, oh yeah. It's the 20th.
20. Okay, so there's still more time. We don't have to worry. So right after coming from spring break, we want an exam or anything. Okay, so we have been doing relativity. We talked about Lorentz transformation for quite in quite detail, more than what I typically do here in this course, and what we have seen is that a quantity like this dt squared plus dx dotted with dx remains the same under Lorentz transformation. Correct, is that? I have been using z square minus c square t square. But immediately you make this z small differential tiny element dz, and that becomes dt. So the same idea, and that remains the same. Now, since this remains the same, you say this is a constant. Right? That's a constant. That's how you will proceed. But this constant, now I can choose this to be a positive constant or a negative constant, and that's my choice, right? Everyone's choice. And that's the choice I was talking about a few minutes back, that particle physicists like to call this a negative constant, and general relativity reasonably consistently they try to do it as a positive. And here, what are we going to do? What are we going to, okay. Or maybe I should say, no, that's not, constant is not where the difference comes in. After I choose the constant, I can have consistently say this is positive and this is negative. I will do that. But you can also say the x dotted with the x minus of c square dt square is equal to a constant, which is equivalent to saying it is a negative one. But you always, if you stick to this as your metric, so this plus and minus that comes in, that's called a metric. So this will be called, so this is -1 plus 1 plus 1 plus 1, right? That's the convention here, and this one is +1 -1 -1 -1. What that means is when you measure distances, it is minus c square dt. Yeah, that's what I wrote that. Is that clear? What that? So this is called a sign convention for a metric. Either way, you can work with it. You're good. But we will use the top line. Okay. So positive for space and negative for time. Is that clear? Did I answer? Clarify? Okay. So we are now defined what this is. So let's put a variable to that. We will have mostly we are going to be working with particles that are moving around. They are physical, so they travel in a causal way. So they will all be time-like. So this is expected to be of the kind minus c square tau square. Is that clear what I mean? That's because if a particle is moving a certain distance in a certain amount of time, it has to be causal. It has to be going slower than speed of light. Or here, this is c dt, dx as a vector magnitude of that. This is a particle moving, and that is d. The length of this is d tau, right? It's c d tau because it's a length. And it has to be always time-like because the amount of distance it travels is smaller than the amount of time it takes when scaled with s. So we are talking about this to be the path of a particle now, displacement of a particle. That's what that represents at this point. Okay, so that's a very special configuration. Any space-time point satisfies Lorentz transformation. But these are space-time points which describe the path of a particle, the world line of a particle. This minus c square dt square, that's a time piece here. This is called, this is tau, d tau, or tau is called a proper time. We will like to call this, after scaling with time, speed of light, that will be ds. That will be our notation, and s will be often the scaled proper distance, if you want to say, but that is related to the proper c times proper time will be proper distance. Okay, is that notation clear? Yes.
What's the vector itself on the c d tau? The vector is es.
Vector. Tell that again.
On the diagram, the vector. actually.
Oh, yes, this is, this is C d tau, right? This is the length. This is the length, okay, how about this? This is C dt. This is dx. Right, and the length, the Minkowski length is C d tau. Do you mean whether it is minus or not?
No, the whole thing, the whole. vector.
Yeah, this whole quantity is that's not a vector, that's a length of the vector. Like the length in this sense, like. So is that clear?
Is it also equal to distance like ds?
Yeah, or C times d tau is ds, that's it. Just a notation.
So we use the constant p tau, meaning like in a certain time, if the particle travels. So,
This is truly a time, right? Because it's time-like.
so
It is
okay, because it is a time, we use the constant as c square d tau.
correct.
Therefore, is again is equal to d square.
Because I'm going to use this. But interpretation-wise, this is better. Physically, it is a time. It is called a proper time.
So here d square is proper.
So ds is nothing but C d tau. That's a notation. That's just
It's not a distance, right?
it is a distance,
Oh, yeah.
right? It's a distance,
Oh, yeah.
but it's related to time. Like it's mostly governed by time, but it's a distance, right?
Yeah.
It's just by units, it's a distance. Right? And often, in almost all these fields, both general relativity and particle physics, they love to use C equal to 1. But I have been, and even in the whole of this course, most of the time C is equal to 1. They love to do that. But I have been trying to use SI units as such completely. I will stick to that. I'll use SI units, which is hard because I have to decode all this textbook, but it's reasonably easy to do that once you get used to it. It's reasonably easy. And the only reason why they set C equal to 1 is it removes a little bit of clutter from the equations. There's a lot of theory we are going to use. So there's a little bit of, I think it's very little bit if you write it in the right way. There is very minimal input of C then. So I feel it can be without significant clutter in the equation. So I'm going to keep it, even though I was trained for not using for setting C equal to 1. So sometimes you will see me setting C equal to 1 here and there, and warn me the moment dimension is not working. That means I'm setting C equal to 1. So that's that point, that why ds. So because if d tau C is equal to 1, then ds and d tau are the same thing. You don't even have to call it. Okay, but that's just definition for any other question. Yeah, so that's our starting point, right? This is our displacement, if you want, and that's ds. And our goal, remember, we agreed upon that time is not a good variable to compare or talk about. Position is not a good variable to talk about, because if you experimentally measure these quantities, they won't match, right? Then we have to use Lorentz transformation to match them. How did you do them, and so on. But instead, if you start measuring ds, it is good. Or if we talk about ds, they are called Lorentz invariant. In every frame, the proper distance will be the same. So the general theme in special relativity is to discuss about quantities which are Lorentz invariant. Then we don't have to talk about this relativity at all. Right? So talk about Lorentz invariant quantities, and that's ds. And now we want to build the whole of kinematics. So what is kinematics? Like, how do we work? So we have time, right? Remember Newtonian physics, right? So just a quick crash course on Newtonian physics. So Newtonian physics is, first you say there is a time, you never define it, you just say that there is a monotonic function which keeps increasing. The only feature necessary for time is that it should not go up and down, right? You always monotonically increase in time, you cannot go backward in time. So that's pretty much what we say. We never define time itself, and we are not going to define time here either. So time will remain a just an intuitive parameter. Same thing with x as a, so let's say a vector position, which is a function of time. As time goes, position of a particle changes. These two are pretty much input of the theory. Give me the time, give me the position, and then you start defining velocity. Velocity is defined as a derivative of position with respect to time. Right? That's the first thing that we do in back in introductory physics. Next, we do acceleration. So you say that derivative of velocity with time, and that's your kinematics, right? So we pretty much say that motion can be described in terms of velocity and acceleration. And then we argue that velocity is not really a good description for motion, because I can always go and sit on the particle and suddenly it is at rest, right? So rest is not really a true concept. It is a frame dependent concept. So you say that acceleration is what describes motion, not velocity. Acceleration is what describes motion. And Newton came and said that acceleration is assisted by forces, right? So vector sum of forces. So you identify the forces, and it is resisted by the mass, right? If you have more mass, you don't have, it's not easy to move things. So motion means acceleration is held by the forces, and it is not inconvenient to move if you have a lot of mass or inertia. That's your Newtonian physics crash course, right? In 2 minutes of Newtonian physics. But now we would like to say, since we have this idea that time and space are two pieces of a Lorentz invariant quantity, can we redo this Newtonian physics in terms of what we have learned as something that is invariant, like Lorentz transformation, which respects Lorentz transformation as much as we can. We will not change the definition of velocity. Definition of velocity will remain the same. Note that V does not change. Acceleration is not going to change. Whatever we mean by velocity and acceleration, it's distance over time. That's going to remain the same. But what we are interested in is that what are the invariant concepts related to velocity? Since velocity, it's not meaningful to measure velocity. At least we cannot compare them unless we transform, do the specific transformation. So what is the invariant quantity related to velocity? What is the invariant concept related to acceleration? And so on. Like that will be our goal. So at least in the beginning, that will be our goal. And then what is Newton's law? How does Newton's law read in a Lorentz invariant way? So what should be, or how should I modify this equation so that I can use, I can find relativistic methods to solve a problem. And then we will solve that for electric field and magnet, charge in electric field, charge in a magnetic field, and that will connect us with electromagnetism, and then we'll proceed. So how do we go about measuring or defining the invariant concept related to velocity? We go back here and let's define what we will call a 4 vector. So I think we did this last time. So 4 vector, 4 position vector. So not 4 vector, 4 position. Which will be x alpha. Remember, Greek letters run from 0 to 3, right? 0, 1, 2, 3, and Latin indices go from 1 to 3. This will be c times t and x. Remember, what this means is that x0 is c times t, and x1 is x, x2 is y, x3 is equal to z, and it also means that x0 is equal to minus ct. Is that clear? I mean, we did this last time. So all that is inbuilt in that, which immediately says that a differential element associated with the 4 position, a 4 differential position if you want, is c times dt times dx. And the moment you have this, one convenient thing to do is divide it out by time. We know time, divide it out by time. Remember, this is like before I do the division, this has this feature. What is that equal to? Dx alpha equal to?
Why not? Cancel out.
Cancel.
Well, not cancel out.
It's
This is a-
0 and 1, 2, 3.
Yes, 0 and 1. So basically it is minus c square dt square plus dx dotted with dx. That's this. That remains the same, right? That's the whole idea. That if I construct a 4 vector, its length, this is its length, Minkowski length, remains the same in every frame. Clear? Like in rotations, if I have a dx, scalar product remains the same. This is the scalar product. Like we do A dotted with B, this is the scalar product in space-time dimensions or Minkowski space, if you want. Okay. That's what you, the moment I write this, you want to think of this, right? But that's both time and position in it. Now, if I have such a quantity, I could do, so let's go in here. This is just playing around. This is not the correct thing I want to do. So dx alpha by dt is also a quantity, right? Why not? If I have a differential element divided out by another differential element, I get a derivative, concept of derivative, and that's equal to c and v, right? Is that, okay, let's do this slowly. So I have c dt dx over dt, right? What I mean is that I will divide out each one of them by dt. That's equal to c and v, right? V is dx by dt. That's your standard velocity. I'm not going to change the definition of velocity. Velocity is distance over time. It's small instantaneous velocity. One would think that, oh, I built components, right? 4 components, 3 components of V, 1 component of C. But just because I have a 4 vector doesn't mean that it transforms like a 4 vector. Right? These are 4 components now. Right? If I were to transform this, this is not a Lorentz invariant quantity. You'll have to show that it's not a Lorentz invariant. So just because I have such a quantity doesn't mean that it's Lorentz invariant. Why is it not? The numerator is Lorentz invariant, correct? The denominator is not a Lorentz invariant quantity, so it's not expected to be Lorentz invariant, even in the naive way. When I'm dividing by some, if I make a transformation, dt will change, and this whole quantity will change. So it's not a convenient way of deriving. So this is, but the idea is this, that the moment I have a displacement, a 4 displacement, what's the associated invariant concept like velocity? So this is not what we do. So we will divide it by something which is invariant, and that is ds. So now I'm going to define a 4 velocity vector. Just an abstract concept, something that will be invariant under Lorentz transformation. So u alpha is going to be a 4 velocity vector. I start with dx alpha and divided by ds this time instead of dt. And I was motivating that, oh, why not do that dt, but dt will not transform like an invariant, or it won't be invariant, or does it? It's not a Lorentz 4 vector. What's the dimension of this quantity? That for velocity I'm trying to define, but what is the dimension of this quantity here?
Dimensionless.
It's dimensionless because ds was distance, right? The distance on the top, distance on the denominator is not, it's dimensionless. I'm defining a velocity, I would like it to have the dimension of velocity, so multiply it by c. So, so that's going to be our fourth velocity. What is that equal to? Pretty much divide this out, so this is equal to c. C is there outside, so that's a c dt, so that's c square dt by ds and dx by ds.
Is this invariant under Lorentz transformation?
Yes, we will show that. Okay, for now, we don't know, but I'm going to build a Lorentz invariant quantity and show that this is actually Lorentz invariant. But for now, I'm just using an analytic tool to just expand this out, but it will come out to be Lorentz invariant. Okay. So, what is this equal to? Use chain rule. So this is equal to c square times dt over ds and dx over, so use chain rule. This is dx by dt. That's good because now dx by dt is the old Newtonian velocity. So that's my velocity and dt by ds can come out. So I have I'm missing something.
There should be a C with dx by ds, no?
Tell me, yeah.
In front of
The
dx by ds.
second component. It's C. No, no,
Oh, that is,
the
oh, yeah,
last one.
C, right? Yeah, yeah, that's what I'm missing. Yes, thank you. Okay. So
For the previous one.
previous one too here. Oh,
C.
because I have put that in. Because the dimension of C has to be there, that's dimension is good. Okay. Thank you. So I can do, yeah, let's just leave it like this side, you know. That's not very, there's velocity in here. That's the only thing that's familiar at this point, right? This is dx by dt is velocity. And there is some dt by ds. So let's explore what this dx by dt is. So we'll go back to our equation there. So that's minus ds square is equal to minus c square dt square plus dx dotted with dx. This is for a displacement of a particle. We are interested in a quantity dt over ds. And since these are differential elements, just divide it out if you want. So this we can write this or not divide it out, just take it out maybe. So that's 1 minus 1 over c square dx dotted with dt dotted with dx dotted with dt. That's velocity, right? Because we're talking dx is a displacement, that's velocity. Dx by dt is velocity, so minus ds, or minus goes away now, right? So ds is equal to c times dt times square root of 1 minus beta dotted with beta. If you want, that's just beta square, no big deal. Even better, that's a gamma, right? If I write this 1 minus beta square, that's gamma. So gamma times ds is equal to c times dt. Okay, gamma, remember, is so this is 1 over 1 minus beta square. And beta, remember, is as a vector is v over c. Okay. So if this is true, c times dt over ds is equal to gamma. So when I do this chain rule, I know that it will always give me this gamma factor, which is also called the Lorentz factor. Often we will use the word Lorentz factor. Remember, gamma is always, so this is always less than. Magnitude is always less than 1. Beta is always less than 1. This is always greater than 1. 1 minus beta squared. It's always greater than 1. So in that notation, then I have this is equal to C times dt over ds is gamma. So I have C times gamma. And this is gamma times velocity v. Or if you want, you can also think of it as gamma is coming out, so C times V. So that's just a 4 vector. Remember again, I would emphasize that velocity, when you really think of a particle's velocity, the way we understand velocity, that is still V there. That is still the same old velocity. It's just that now we have found a construction where if you put these things together as a distance or a Lorentz invariant quantity, this will turn out to be Lorentz invariant. But let's see what that is equal to. If it is Lorentz invariant, what is that equal to? Is this really Lorentz invariant? So we have to calculate U alpha, right now. But we'll do that. But any question before that? Lorentz transformation was for position and time. And now we have built a 4 vector associated with velocity, and the idea is that the magnitude of this, the Minkowski length associated with, is an invariant quantity. And then you would say that, oh, what should I measure? Like if I'm doing an experiment, what's the quantity that I should measure instead of velocity? Velocity cannot be measured because then you have to do Poincare transformation to get that, or Poincare velocity transformation or the Lorentz transformation to do that. So instead you measure this, so you might think that that is a convenient object. So what is that equal to? So we calculate this. So we start from here. So how we do this is first write C times gamma and then write the negative of that, right? That's how you go by that, right? The time component switches sign and then plus gamma times V dotted with gamma times V. My gamma is difficult to write. Is that clear? Like in our simplistic way of using the Minkowski vector, I'm not emphasizing on the contravariant covariant part. This is just got by the take the contravariant time component, multiply it with the negative of the contravariant time component, and then multiply the square. So that's one way out. But it's the same thing that you would do the other way also. Okay, clear? So this is equal to minus C square gamma square minus V dotted with V and C. Something is wrong there. So dimensionless C square gamma square and 1 minus V dotted with V C. What is that equal to? What is that equal to? Minus C square, right? Because this is 1 minus beta square. Very good, right? And gamma square is 1 minus beta square, that cancels out. That's minus C square. Okay, so I went by saying that there is an invariant quantity associated with velocity. In fact, it is the speed of light itself. Like anything that moves, what remains invariant associated with that speed or the velocity is the speed of light itself. So whatever happens between these two components, they only compensate each other. The total of that is to remain the same. That's what we learn. Again, remember, the particle is moving. It moves the same old way, velocity is V. But this quantity together have to balance each other. we have found that there is a gamma and a gamma times velocity. It has to happen in such a way that they always compensate each other. Correct? Clear? There is a negative sign here. What does that mean? What's the essence of that negative sign?
Opposite direction.
Opposite direction of movement.
Oh, wait.
Think of your homework.
Yeah, if it's negative, it means it's time limit.
It's timeline, right? So the invariant concept associated with U is timeline. So U alpha is timeline. Which is understandable. That's a tangent we are talking about. World line is a particle that has its tangent always timeline, right? It's a causality that requires it, or more than causality. Just the fact that it should go smaller than, slower than speed of light. That causes that negative sign. Clear? Yeah. We can, of course, so this is all you need to know about forward velocity. And next is, of course, now we have forward velocity, go to forward acceleration, right? You're doing Newtonian physics, but we are now doing it in the relativistic form. Time, position, velocity now has been generalized. It has a time component also, which is gamma. Right? Gamma is a time component of velocity. Right? Remember, it has to be a scalar, or scalar in the sense of scalar in the sense of rotation. So gamma is the time component of velocity. And together, gamma and beta, so this is nothing but beta, right? Gamma and beta gamma, it's basically a content of Lorentz transformation that it remains the same. Take a derivative again, we will get acceleration. And then we will be ready to associate it with force. But let's take a detour, like that is in this construction, somewhere we encounter momentum, right? So P is equal to M times V, right? In our Newtonian description, and energy is half mv squared, kinetic energy is half mv squared, right? And that has this feature that I don't need acceleration for that. Right? When I'm dealing with kinetic energy and momentum, I can define things in terms of velocity itself. And I've already done the job of velocity. I have taken care of how velocity transforms, or what's the invariant quantity related to velocity. So I'm ready to handle momentum and energy. For dealing with force, I have to take another derivative, but I'm going to delay that. And let's talk about momentum and energy and see what we can do. So let's go to this board. Oh. So summary is that forward position is our forward displacement. Forward displacement is dx alpha equal to CPT and CPT and dx. And for velocity is u alpha, which is dx alpha over ds times c, equal to c times gamma and velocity times gamma. Okay. Let's define for momentum as for momentum is simply like mass times velocity typically is for momentum in Newtonian physics. But here let's define momentum P alpha is equal to m times u alpha. This is for momentum. That's straightforward. M times U alpha, and this is the mass of a particle. In popular physics, often you will hear that mass changes with velocity, like E is equal to mc squared, especially. Like you often see this, and you say that, oh, m is basically dependent on velocity. That's not what we are saying. This is a constant. M is the rest mass of the particle. This doesn't change with velocity. Okay, so maybe I should emphasize that. M is the rest mass of the particle. This is the usual definition that we have for particle, sorry, mass, that we use in Newtonian physics. And this is not going to be velocity dependent. It doesn't change with velocity. M remains the same. Okay, so, or for now, it is just a constant, and we will show that M remains the same. It is going to remain the same. Okay, clear? So that's our simple extension, right? This is, I just have to multiply this by C, so it's MC gamma and MV gamma. Just a small extension of velocity. But this is, until at this point, this was just manipulations, right? We were actually figuring out what are the invariant quantities. But at this point, Einstein made a leap. This is where Einstein's physical interpretation comes in. At this point, he says that this is the momentum. Now he's changing the definition. So until here, this was algebra. I'm just building things. But Einstein's physical interpretation is, so this is physical interpretation, or Einstein's physical interpretation. So Einstein's physical content or interpretation, if you want, right, is that this is the energy and the momentum of the particle. So P, this is the relativistic, that's equal to mv gamma. This is different, right? Remember, P classical, P Newtonian, P Newton is equal to m times v. Different. Okay, now we have velocity. I did not change. Acceleration also we will not change, but the momentum definition changes. Energy also will change, the kinetic energy of a particle. Here we don't typically say kinetic energy because kinetic energy by definition, right? The word has kinetic in it. It means that it is moving, and we will see that even when it's something is at rest, here we could have energy. Just because it has mass, you will have energy. So you usually don't use the word kinetic energy from now onward, but that's the analog of kinetic energy. What is this equal to? MC gamma. What's wrong now? What is wrong in this equation?
Dimension.
Dimension, right? So m times c as a dimension of momentum. So you would like to have the dimension of kinetic energy. You put in a c, so let's say E over c, or put it on the other side and put that as c squared. Okay, so this, remember, kinetic energy. So kinetic energy of Newton is half mv squared. This seems to make sense. mv, you just have a gamma, but that is half mv squared in here. It doesn't seem to have that signature at all, but let's move on. Okay, so this is new, right? This is the only difference, only input that comes in. This is, if you want to say magic, or this is the postulate, this is what Einstein is popular for. Okay. Before we proceed, I'll come back and say what the connection between this. We will talk about that, but that is the moment you said P alpha. Now it is energy and momentum. So you know what you're saying is that P alpha with these definitions, P alpha is energy over C, and the momentum, the new definition of momentum, which is the, I mean, from our understanding now, it's a correct definition of momentum, right? This is only an approximation in that sense. So Same idea of velocity, but by multiplying by mass, I have developed the idea of 4 momentum. And that is a Lorentz invariant concept. Now what we are saying is that energy and momentum should not be measured. If you measure the energy of a particle in your lab, compare it with someone else who has done the experiment in another galaxy, you won't match. Right? It's not expected to match. It's a time component. Right? If you measure the momentum, compare it with someone else, it won't match. Remember the whole of quantum mechanics, we talk about energy eigenvalues, and also if you match it, if you're doing relativistic comparisons, let's say your friend is going at relativistic speed in the next door lab, then your answers are not expected to match. And you don't have to be going at relativistic speeds, even if you're driving on an interstate at 70 miles per hour. If you want your GPS to work, you have to go at relativistic speeds and come back from the satellite for it to work, right? So that within 1 meter, you have to travel that much. So it's very significant. So these two cannot be matched. Then what should we match? So you don't want to match energy, you don't want to match momentum. So what should we match? Again, we go by invariant idea, right? U alpha, U alpha. So what you should match is the invariant quantity associated with that. And what is that equal to? Immediate answers? Yes.
Minus a square rho c square plus.
Yeah, that's correct. What is that equal to? I'm asking. Immediately you can do it. Right. Because it's this. This is the same as mu alpha times mu alpha, right? U alpha, I know is p squared, right? That's equal to minus mc squared, right? That's the invariant. What is invariant? Mass.
M squared C.
M squared c raised to 4. Sorry. Oh, m squared c squared. That's it. Right? Isn't that right?
Yeah.
I think so. Right. So what remains the same? The mass. Like energy can change, momentum can change, but they will change in such a way that mass remains the same. In every observer, in any frame you go, energy and momentum will balance each other in such a way that mass is the same for it. Tell this more explicitly. So this is minus E squared over C squared plus P squared. Right, minus E squared plus P squared, that's equal to minus M squared C squared. Right? Rewrite this and you get E is equal to P squared C squared plus M squared C raised to 4. That's your kinetic energy formula in terms of momentum, like in Newtonian physics, there is this connection, right? So kinetic energy is equal to P squared over 2m. Right. This is the Newtonian analog of kinetic energy is equal to P squared over 2m. But what's the connection? We will see that in a few minutes. Okay. Often this is relativity became very popular, or one of the few equations that became very popular among the normal non-academic people. And it was very convenient to print these equations on a t-shirt, and that's too much of algebra there. Square root is too much for printing on a t-shirt. So this is often printed as mass effective, and with the effective taken off, times c squared. When you type it like that, it's understood that m is changing with velocity, but we are not going to use that. Often in popular textbook, almost none of the serious textbooks keep it m as changing, but often it is convenient just for notation purposes, so we won't use that. So energy is momentum and mass dependent, and the invariant idea is that momentum changes, energy changes, but together they don't change. Okay, that's the key feature in there. Energy transforms, energy probably contracts or dilates, whatever it does, momentum contracts or dilates, but together they remain the same. That's the basic idea. That's also, see, so there's in some way, there should be a connection between these two, right? So let's very quickly do that. But before I proceed, any questions or comments? Yes, look.
Why do we use in 9-time critical energy is equal to MC?
Again?
Energy is equal to MC. Why did we use that in 9-time critical?
I still did not get it. Repeat.
The energy is equal to MC we use in the first place. Why did we use that?
Oh, these two
Given
is not given. This is a postulate. If you want, this is this is equivalent to saying y is p momentum is equal to mass times velocity. Like somewhere Newton's law is a postulate, right? It's a law. So we are changing the definition of momentum. That's like Einstein changed the definition of momentum, changed the definition of energy. And the idea is that if you do this, then it works out well. Like now, if you do Newton's laws using these momentums, it gives you better or correct calculations, or even better, like Newtonian physics has this problem that if you shine a light, flashlight, then its velocity should change just because I'm moving. Right? And now you won't have those problems. That's the main idea. Maxwell's equations are consistent with Newtonian equations from this point on after you make this change. So this change is what is needed. So if you think about what did Einstein change, that's the change he made as far as user level goes. Of course, he changed the way we look at space and time, like space and time are invented ideas, how they transform. All those things are contributions from Einstein. But at a user level, when you go to the lab, how do you want to think of, oh, where does Einstein's results affect me? This is where it affects. Like we use momentum and energy in whatever we do in every lab, doesn't matter which lab. GPS does that. So that's where that affects. That's that input going in there. Reasonable? Okay, any other comments? Okay. So at some level we should be able to get back our Newtonian equation, right? And I said this is kinetic energy, but I didn't use the letter K there, right? It should have been okay to use K, but you will notice that it is not truly the kinetic energy. There is some more piece to that. Okay, so let's do. So let's start with gamma, and gamma is nothing but 1 over beta square, right? Square root of that. Let's expand it. We are wanting to ask what if beta was small, what if velocity with respect to c was small, if beta was small compared to speed of light. This is nothing but 1 minus beta square raised to minus half. Expand binomially, this becomes 1 plus 1 by 2 beta square, plus there is a next term which is order beta raised to 4. By this I mean that whatever is remaining is order of beta over 4. Is that clear? I'm not writing that specifically. That's a whole series there, beta square, beta 4, beta 6, and so on. Whatever that is, surely it is there's a beta raised to 4. If beta is, for example, often electrons go around in an atom at 10 raised to 7 meters per second, then beta is 0.1. Right? If velocity is 10 raised to 7 meters per second, and that's pretty high. But then beta square is equal to 0.01. I'm keeping that. Beta raised to 4 is 0.001. So unless I'm doing an experiment which has 4 significant digits in it, I'm safe at dropping this. Right? So most of our experiments that we do in the lab, which are called non-relativistic experiments, it is hard to take care of this. Unless you're doing a GPS measurement, then that 4th significant digit is important. because that will decide whether your car is 10 meters or 50 meters away, right? So we are in this regime, so 0.26 digits, let's say. So we're going to drop everything with beta raised to 4, right? So come back and put that in momentum. So P Einstein, for example. So this is P Einstein. It is the default. Let me just say P, right? So P is equal to M times B, which is P Newtonian, times gamma, which is 1 plus 1 by 2 beta squared plus higher order terms. This is 1 and this is 0.01, like this is small. So I can neglect this. Under what conditions is this true? This is equal to MV plus MV times beta square, order beta square. If you want, that's how you write it for the dimension say, that's all. So it is MV itself if you're going very slow, right? If you're going very slow, there is a mass multiplying mass times momentum multiplying by that. And in that case, you can set that to be the Newtonian. So what about energy? So energy that we set is equal to, where is that? MC square gamma, right? So it is MC square gamma. So it is 1 plus 1 by 2 beta square. Let me write that as B square over C square. Plus order beta raised to 4. Or let me just say plus. Yeah. So it's higher orders. Now, if you notice, I have MC square coming in. Second term, nicely, C square cancels out. Newtonian physics have no understanding of speed of light. So it's plus half MV square plus so on. This is Newtonian kinetic energy. But now you're left with a new piece to the energy. Like what we always think of kinetic energy, which plays a very fundamental role in physics, is that forces are used to convert energy from some form of potential energy into motion, which is considered kinetic energy. Kinetic energy is motion or energy associated with motion. But now you're saying that there is energy associated just because you have mass. Like just because there is the existence of mass, there is an energy associated with that. Remember, energy can be transferred, potential energy can be transferred to velocity, right? Motion, right? That's the main idea of energy, that you can transfer things, mechanical energy. But now there is this idea that mass, just mass, if you destroy mass, you can create motion. Right? And that's the idea of atomic energy. Like this is where the idea of atomic energy comes in, that you destroy mass somehow. Like how you do that, that's a complicated or you need to have ideas on that. Then comes the idea that bigger atoms, when 2 neutrons and protons come together, there is a deficit in mass and so on. That is all interesting ideas there. But the main idea here is that just because there is mass, there is energy, and that energy can be converted to kinetic energy. Right. So this is the rest energy. That idea was not there in Newtonian physics. That's a new physics. And of course, this was used very quickly, used in a horrific way, but it has been used and properly applied. And yeah, bad parts of how we use it, but nevertheless, nice interpretations of this. So that's the new feature. And that again, we see that here, right? This is the rest energy associated with or square of the rest energy. This is the moment, like P squared, C squared. And that's the bifurcation from the standard Newtonian relativity or non-relativistic physics that we have. Okay. Any questions here until now? Okay. Still, it is not, if you're working with energy, most of the time what happens is that if you remember the way we do Newtonian physics, even though we learn how to find motion associated with forces, right? We find forces, then related to acceleration and describe motion. We learn very quickly that system is described by energy more than force, right? In a sense, energy is more fundamental, or force is a manifestation of the fact that the system is trying to minimize its energy. One general law that whole of all science, chemistry, physics, biology, if you don't understand what you're doing, what you should do is that try to minimize the system. Nature minimizes the energy. That's one thing that is going. It is manifested as if that is a force. Remember, negative change in potential energy, force is equal to negative gradient of potential energy is a force. It works only for fundamental forces. You need to have a potential energy associated with it. Gravity works, electrostatics works. How many potential energies have you come across? 4. So only fundamental forces. You don't talk about potential energy associated with friction, only conservative forces, right? But most of the time in physics, we are doing conservative forces. So potential energy is good. So energy works very nicely. We don't have to worry about force. So most of the time, this is sufficient. If you work with energy, have the corresponding potential energy, this is sufficient to do a lot of physics, right? If you're working in the energy ideas. But we would like to talk about electric field. We would like to talk about what happens to a charge when you place it in an electric field, especially in an electric field, because if you do elementary introductory level physics problems, when you put a charge in an electric field, which is even very small, 1 Newton over Coulomb, within a fraction of a second, within a nanosecond, it reaches relativistic speeds. So we better know how to handle relativistic physics, because then we can explain that we don't have to talk about particles going faster than speed of light. So we would like to talk about what happens to a charge in an electric field, in a magnetic field. So we need to find the acceleration. So we proceed and calculate that or define the 4 acceleration, right? So let's keep this here. So 4 acceleration now. So 4 position vector, 4 velocity is u alpha is equal to c gamma v gamma. And for momentum, this involved a postulate. E alpha is equal to energy over c and p, which is also mc gamma and v gamma. Let's just multiply by that. And we are to do 4 acceleration now. For acceleration is going to be a alpha. Remember, this is not the acceleration. Acceleration will be the same old acceleration. A is change in velocity over change in time. This is our the standard acceleration will remain the same. It's just that measurement of this acceleration may not be a good or may not be easy, but that's going to be our acceleration when we think of it in physical terms. That's going to be our acceleration. We are going to define 4 acceleration. It's going to be du alpha over ds. And what's the dimension of du alpha by ds?
Distance. Then
That's
it's
supposed
distance.
T minus
1/s.
T minus.
T minus 1/t, right? This is velocity.
Oh,
This
that's-
is a distance. So distance over time and divide by distance, so 1/time, right? But acceleration should have the units of velocity over time. Right, so I'll multiply by c, right, just for dimensional reasons. Same idea as earlier. So our 4 acceleration is going to be defined in this manner, right? U alpha is this, right? So put this in here. So there is a c square. Derivative of gamma. Remember, gamma is a velocity dependent quantity, right? So gamma had beta inside it, so it's a velocity dependent quantity. And ds. That's this here. And then I can now differentiate velocity or gamma. There are 2 pieces in there, right? Maybe I should do this in 2 steps. So this is the same as c times d by ds of c times gamma and v times gamma. Because u alpha is this. So this is equal to c squared derivative of gamma with ds. And this is, now I have to take the derivative of both velocity and gamma. So this is c times dv by ds times gamma plus c times v times derivative of gamma. That's clear. dv by ds is equal to the c square d t over ds. We always use chain rule. dt comma c dt by ds. Remember, c dt by ds is gamma, right? Times dv by dt. That's your acceleration. Acceleration is sitting somewhere in between this expression, but that's the transformation we are interested in. And then there is a gamma again, plus c times v and dt over ds and d gamma over dt. Remember, c times dt over ds was gamma. Use that in here. So we have c times gamma times derivative of gamma, time derivative of gamma. This is now a gamma square times acceleration. Acceleration, notice, is derivative of velocity with time, plus gamma or velocity times gamma times gamma over dt. Okay. Already crossed the time. We need a quiz for today. Remember, u alpha is minus c squared. Right? That means it's time-like. Without going into this, take a derivative with ds. That's du alpha, there is symmetry in there. So that's the same as u alpha is equal to 0. C is constant. So acceleration times u alpha is equal to 0. Use your homework to conclude, what can you conclude about A? What is the nature of A? Is it time-like? Is it space-like? Is it light-like? Okay. So U is time-like. A alpha times U alpha is equal to 0. So. What is A like? What is A alpha like? By that I mean, is it space like, time like, or like? Use the homework that you did.
Do we assume there's also a C included?
Oh,
Oh, never mind,
because this goes to 0.
but yeah, but you can't do that.
Yeah. Okay, thank you.